Welcome everyone to GIA Knowledge Sessions, a series of talks about gemology drawing on our decades of research here at GIA. We're very fortunate to study and learn from the world of gemology, and it's part of our mission to share our discoveries with everyone. I'm very excited to kick things off today. I'm Troy Ardon, I'm a research associate here at GIA, and I'm joined by Dr. Sally Magaña, the Senior Manager of Diamond Identification, and she's going to talk to us about the science behind pink diamonds. Now, before we get started, just a bit of housekeeping. Everyone attending this is automatically muted. If you have a question, feel free to submit it using the question and answer feature somewhere along the bottom of your screen. Ask questions as we go, and there will be a Q&A session at the end. We will also be sending you a recording of this session later today, and that message will also have a survey that we would love for you to complete. And with that, I'm going to pass you over to Sally.
Hello, everyone, and I'm very glad that you're here with us today. A few weeks ago, we started off our series discussing fancy colored diamonds. Back in July, I gave an overview of those defects that bring about fancy color in diamonds. 2 weeks ago, my colleague, Dr. Mike Breeding, gave a talk about natural green diamonds, and today I will be discussing natural pink diamonds. I will start off the talk by showing some of the remarkable pink diamonds that have been created through a collaboration between Mother Nature and some very skilled polishers. We have some famous diamonds here, we have some historic pink diamonds, and we can see the beauty that is created when science and artistry converge. This slide shows the color distribution that can be seen within pink diamonds. Along the top row, we show the color saturation for straight pink diamonds from very light all the way to fancy red. And on this middle row, show the impact caused by increasing amount of brown color or an increasing amount of orangey color. And then on the bottom row, we show the impact of increasing amount of purple color. So there's a lot of different hue descriptions on the screen. We have pink and red, brown, orangey, and then purple. And all of these were coalescing into what we're calling the pink family. And the reason we do that is because all of these show a very similar cause of color that we'll be discussing throughout this talk today. The hue distribution in what I'm calling the pink family is shown in this slide. About 40% are pink straight pink diamonds, about 28% are pinkish purple, the purplish pink, 17% are brownish pink, the pinkish brown, 10% have an orangey component, 3% are straight brown, 1% are purple or with some other color modifier, and then 0.9% are red. This slide shows the weight distribution that we see within the pink family. These data are divided up into 0.1 carat increments, and we also subdivide each of the columns by the major hue that is seen in the diamonds. And a couple things should come out immediately from looking at this slide. One is that the vast majority of pink diamonds are less than 1 carat. We see the vast majority of stones over in the less than 1 carat range. But we can also see some spikes at the weight thresholds of 1, 1.5, 2, and so on. So while the cutters certainly want to maximize that face-up color, they will also take into account weight considerations as well. I'm going to start discussing the color centers that we see in pink diamonds. Over on the left, we have what are called the GOLCONDA pinks. These are very rare in natural diamonds. The color for these come about from nitrogen and vacancies coalescing together and creating a pink color. It's very rare in nature, but it's actually very common among treated pinks. Most treated pinks and most treated lab-grown pinks get their color from this mechanism. I will spend most of my time talking about this mechanism over on the right, in which the pink colors derive from an absorption band that is centered at 550 nanometers. It is the cause of color in 99.5% of natural pink diamonds. And we don't know all of the details about what causes this pink color. We don't know the precise defects or what is exactly put into the diamond, but we do know that it's related to plastic deformation. And the process is very similar to how we get brown color in diamond as well. So these brown and pink diamonds are rather close cousins to each other. So since plastic deformation is how we think these diamonds get their color, I'm going to spend a little bit of time talking about that. We are not sure about many more aspects of the mechanism, and with that in mind, I'd like to explain a little bit about it and the geologic forces that are creating that in the diamond. Over on the left is an illustration of the mountain building scenario that typically causes deformation. However, this may not occur in all localities. This illustration in the middle shows that pink Argyle diamonds have eclogitic inclusions, and that places these diamonds at about 1250 degrees Celsius while they're forming. And diamonds at these high temperatures will respond to stress by undergoing plastic deformation and getting that little kink that in the diamond structure. And then over on the far right, I'm showing a fun metaphor illustrating that at room temperature, materials can have very different reactions than what is experienced at high temperatures. GIA maintains a database of submitted diamonds. We surveyed all natural diamonds that contained pink, purple, or red as the dominant color. We also included many brown diamonds as well, including those with a straight brown color. At the time of the survey, these diamonds total about 90,000, and the 4C data shown earlier were from those stones. Additionally, 1,000 of these diamonds were randomly selected across all pink color descriptions and saturations, and we studied those in depth. The features in the UV vis absorption spectra, their diamond type, and when possible, their nitrogen concentration. These could then be compared against their 4C data. With all these data in hand, there were many ways to slice and dice the data, and a number of interesting trends emerged. And I'll be speaking about that a lot on these next slides. But before we get to that, I want to give a brief recap on nitrogen-related defects. We spoke about these a lot when I gave my talk back in July, but I'm just going to quickly run through some of the important nitrogen-related defects that we have here. Now, as you may remember, most diamonds as they form, they have nitrogen. They start off with having that as single and isolated nitrogen. And then over time and temperature, while these diamonds are residing in the earth at about 1,000 degrees Celsius or higher, those nitrogen atoms start to move around and pair up. And once they find each other, they want to stick together. They don't want to split apart again. And as we continue along that time and temperature, it's going to eventually reach from this A center, which is a nitrogen pair, to a B center, which is 4 nitrogens and a vacancy. And most natural diamonds are a mixture of those A and B aggregates. And we show that progression over here on the right as we go from increasing time and temperature within the earth. We're starting down here with 100% A aggregates. And as the diamond continues to dwell within the earth, we see this progression to an increasing amount of B aggregates that we can see within individual diamonds until eventually the diamond is 100% composed of B aggregates. So we're going to be speaking about this a lot today, whether a diamond is A less than B or A greater than B, and we can determine all that from the infrared absorption spectra. Now you may be wondering why we're concerned about features in the infrared, because we're trying to look at pink color. But there is a really interesting correlation between the infrared nitrogen concentration, the infrared spectra and the nitrogen concentrations that we detect there, and the resulting properties that we see in the pink diamonds. And then one other thing I want to mention is that as we go along this aggregation pathway from A aggregates to B aggregates, we also get some other defects that form along the way. Those include the N3 defect, which is 3 nitrogens and a vacancy, which creates visible absorption at 415 nanometers, and then the H3 defect, which creates visible absorption at 503 nanometers. Since we'll be looking at many absorption spectra, I wanted to quickly recap the features that we see. On the y-axis, as we go up, we're absorbing more light, and conversely, as we go down, we're transmitting more light. So if you want to read the defects causing the absorption, then you read the peaks. And if you want to see what the color is, then you read the valleys. This red line shows what's happening in the diamond, absorption and transmission, what reaches our eye. So what we're seeing here is a broad absorption centered at 550 nanometers. So when I talk about the 550 nanometer absorption band, I'm talking about this broad band right here at the middle. And that absorption is centered at 550, like most natural pink to red diamonds, and thus the valley of the transmission is in the red part of the spectrum. And this is the resulting color of the diamond. So here on this slide, we're showing several different absorption spectra for a variety of pink diamonds, and you can see their colors vary quite a bit. But they all have one thing in common. They all have this 550 nanometer band. On some, you can see it's stronger and weaker in others, but it's there in every single diamond. And so what we can also see is that there is some variation in the other features that are also present in this diamond. For example, this top spectrum shows also those nitrogen-related defects I mentioned earlier. It has the N3 and the H3 defects. Meanwhile, this bottom spectrum has this gently increasing absorption towards the ultraviolet that comes about through vacancy clusters and creates a brownish color in the diamond. So there are a number of different features that can be present or absent in these diamonds in addition to the 550 band. And we're going to talk about those quite a bit as we go through and keep an accounting of what features are present in each of these diamonds. I'm going to focus in on two very different stones on this slide. They both have the 550 nanometer band, but they have very different colors. I would put these at, say, the opposite ends of the pink diamond family. We have a purple diamond here, and you can on the top, and you can see that we have transmission windows in both the red and the blue. And meanwhile, this pinkish orange diamond is very pronounced absorption from these nitrogen-related defects. The H3 and the N3 defects are causing that to have absorbed within the blue and shifts that transmission window over into the orange and the red. Another thing that might not be quite so obvious is that there are some differences within the 550 nanometer band itself. The purple diamond shows a much wider band than the one we see in the pinkish orange, and it's also subtly shifted to a higher wavelength. So differences within these ultraviolet UV-vis spectra, whether it's very obvious, like the presence of these nitrogen-related defects, or very subtle, such as the distinguishing characteristics in the 550 nanometer band, can bring about very different colors in this pink diamond family. So keep that in mind. We went through all of these diamonds and cataloged whether they had the 550 nanometer band and what other features might have been present. And within those 1,000 diamonds. And this is a little busy slide, so I'm going to walk you through it. Along the bottom, we're showing the saturation of the diamond among those 1,000 that we cataloged. And then we're looking at the population of what UV-vis absorption features are present in each of those diamonds. So like the purple diamond we had on the previous slide that just had the 550 nanometer band, that would be colored in this pink. Whereas the pinkish orange had both the N3, the H3, and the 550 band, so that would be in purple. What we wanted to point out here is that the diamonds that are colored only by the 550 band are overwhelmingly populating those lighter saturations. And you see this dramatic shift within the intense and the vivid colors towards those diamonds that have those additional absorptions due to nitrogen. They have the N3 and the H3 in addition to the 550 band. And it looks to be that that's what's really needed to boost up, to give that, to boost up the saturation in order to give this diamond into the fancier and the intense categories. It really needs that nitrogen contribution in order to create a intensely colored diamond. This slide shows a collection of IR spectra. We showed some on the previous slide, but this shows the full diamonds, and then it also shows a few other examples that did not focus specifically on the nitrogen aggregates. Up here at the top, we show a saturated nitrogen diamond. In fact, there's so much nitrogen in this stone, we cannot determine whether it has the A aggregates, B aggregates, and what the concentration is. We just know that it has a lot of nitrogen. And then down here at the bottom, we have a type 2A diamond, meaning that there is no detectable nitrogen within that stone. And then in the middle, we show a variety of stones that have A greater than B or A less than B, and various nitrogen concentrations. And then we're also able to determine what those nitrogen concentrations are within each of those diamonds. So we did that for all of the 1,000 stones that were used in the survey, and we chronicled what those diamond types were. And I'm showing the summary of those information here on this slide. And over here on the left, I wanted to point out a few aspects of it. One is that among type 2A diamonds, firstly, that there was fully 1/4 of the sample set, 249 out of 1,000 were type 2A. And that's something that I hadn't realized until we did this study, just how a high percentage that type 2As are among pink diamonds. When you look at D to Z diamonds, there's only about 2% of D to Z diamonds are type 2A, whereas among pinks, they are 25% population. Also, you can see that the vast majority of the type 2A diamonds are colored only by the 550 nanometer band because they have very low or no detectable nitrogen, so they're not going to generate those nitrogen-related absorptions also. And then I also wanted to point out this category of A less than B, where the A aggregates are less than the B aggregates. And you can see that there's a large number of diamonds within that category, almost 400. And you can also see that most of those, the vast majority of those, have the N3, have both the 550 nanometer band, and then also N3, H3, or both. So we're seeing we're seeing a lot of features that are necessary to create those vivid and saturated colors that we saw on the previous slide. And then over on the right, I've grouped the diamonds a little differently. The diamonds shown in pink colors are those that are type 2A. The diamonds shown in red are those that are A less than B or type 1AB. And then the diamonds that are in purple are those that are type 1A or A greater than B. And I'll show on the next slide why we made these groupings. But you can see from the diamond typing that there are several segregations within the color for the color of the diamond that we can see. For example, all diamonds that have a red color are in the A less than B category, whereas most of the diamonds that are orangey pink are also in the A less than B category. And we're seeing about an even distribution among the pinks and the purple pinks and the brownish pinks among these three different groupings. This is a busy slide also, so I'll walk you through that. Now, the three different groups that I mentioned on the previous slide are type A less, or type 1A, A less than B, A greater than B, or type 2A, where the A and B aggregates are 0. And for those 1,000 diamonds, for the diamonds in which we could calculate out nitrogen concentrations, we plotted those A and B aggregates on this slide. It cannot include those that are type 2A, which have no nitrogen, or those that had saturated nitrogen, but includes all the other stones. And this diagonal line here is A equals B. So the stones that are to the right of that are A greater than B, and the stones that are to the left of that are A less than B. And you can see from this plot that there's a lot of stones congregated here along this green trend line. And these data also correspond very well with known Argyle diamonds. And in fact, all Argyle pink diamonds are A less than B, whereas most other diamond mines have pink diamonds that are A greater than B if these pink diamonds contain nitrogen. Now, this isn't something that we found as part of this study. It was observed earlier, and I show some of that data from previous researchers in this red box, where the diamonds that are A less than B are from the Argyle mine, and then from St. Helena in Venezuela, and then pretty much everywhere else that has nitrogen containing pink diamonds are in this A greater than B category. So all these groups have distinct characteristics, and all of them are largely mine dependent. So let's talk about some of those mines in the next few slides. I'm going to talk first about the Argyle diamond mine. It's located in northwestern Australia, major supplier of those type 1A, A less than B pink diamonds, and spoke recently with one of their geologists, and they reported that they would cease mining in November 3rd, 2020, and they will process ore for that next month. They do anticipate for closure and rehabilitation to continue for several years. Another major producer are the Siberian diamond mines. Those are principally A greater than B and saturated nitrogen type. That's mainly from the Mir kimberlite field in Siberia, and they're a major source of purplish pink, gray purple, and pink, and then rarely purple, straight purple diamonds. So look at some of these distinguishing characteristics in greater detail. Okay, and when I make this distinction about A less than B being, quote, Argyle, I can't say for certain that those are from Argyle. I can make a very good hypothesis based on production numbers that come from, say, these mines versus others, but we can't say for certain that any specific diamond that is A less than B comes from Argyle. And similarly with Siberia, if we have an A greater than B, considering the production that comes from there, we can make a good hypothesis, but we cannot say for certain. But just try to help keep these A less than B and A greater than B in your mind. I'm just going to call them as, quote, Argyle and, quote, Siberian. So what we're plotting here is the data that we looked at for the stones that were Argyle type, and then we looked at the tone and saturation of those. And we can see that the majority of them are fancy or higher colors. And then among the Siberian, what I'm calling the Siberian diamonds, most of those are in the faint to fancy light or the fancy color categories. So we can see this very distinct differences in terms of the tone and saturation between the A less than B and the A greater than B. And similarly, we think that comes directly from what we can, the VIS-NIR IR absorption features that we see between these two very different diamond groups. Those that are from Argyle, overwhelmingly we see that the 550 band, but we see these nitrogen-related defects as well. In fact, most of the Argyles show this N3 and H3 absorptions in addition to the 550 band. And as we saw earlier, that helps boost up that overall absorption that we see in the stones. Whereas most of the diamonds that are from Siberia have the 550 nanometer band only. And so that's why we see purple color in those diamonds, because it creates a transmission window in the blue. There's no absorption in the blue, but it creates that transmission window. So that helps create a purplish color in those stones. And if you think about why that happens, about why we're seeing these greater amounts of N3 and H3 in those stones that are A less than B, then it can make sense when we think about that aggregation pathway. As we go from A aggregates to B aggregates, we create H3 and N3 centers along the way. So the further we are along that aggregation pathway, the more nitrogen that has been converted from A aggregates to B aggregates, the higher the chances are that you've created some of these nitrogen-related defects in the visible as well. And so we think that's the major reason why we see such a difference in the absorption features and then therefore the saturation in the Argyles compared to the Siberians. Another really interesting thing about these different diamond groups is they have very pronounced differences when you look at them in the microscope. And so this is one of the really interesting things to me about pinks and why I like pink so much is because you can look at these in the microscope, and typically in the pavilion, the cutters normally orient the diamond so that it has even color face up. So if you want to see these graining, then you need to look at the pavilion. But what we can see in the microscope is very distinct to the diamond type, whether it is A less than B, and therefore, you know, from Argyle, it has often this wavy color where you can see that the lines are undulating, they're not perfectly straight. You can also see that we have some very pronounced pink color in some parts of the diamond, and right next to it, it's pale pink, but it is pink, it's not colorless. And then for this A greater than B, the Siberians, you can see that the pink color is concentrated into glide planes that are very straight, very parallel, and outside of those, there is no color at all. It is completely colorless. So you get this candy cane striping in those A greater than B or Siberian stones. And then for type 2A, we haven't talked much about the locality information, but from what we know is that there's all of the pink diamonds that are type 2A that we've heard of, they've all come from the African continent. They've come from different countries within Africa, but they've all come from Africa. That doesn't mean that all type 2As do come from Africa. It just means that the ones that we've known about have come from there. And type 2As are distinct from the Argyle and the Siberian in that they have even color. So it's really interesting that when we look at these diamonds in the microscope, we can infer a lot about the diamond. We can make if we have this wavy graining, from that we can infer that it's A less than B, and we can have a pretty good hypothesis that it's probably from Argyle. And so you can't do that with a lot of other diamonds and know so much about the spectroscopy and perhaps the locality just from looking at it in the microscope. So that's one of the really interesting things about pink diamonds that was really fun to discover. Also, we see similar distinctions between the different groupings when we look at the strain. When we look at this diamond between cross polarizers in the microscope, we can also see very distinct differences between them. So the A less than B, they have that wavy graining similar to the color concentrations that we see under normal lighting. And then in the A greater than B diamonds, the Siberians, we see mottled strain throughout most of the diamond, and it's interrupted by those straight glide planes. And then the type 2 diamonds have tatami graining. They're also very distinct from what we see from the other two groups. So let's learn more about what's inside the diamond. Now, most of these A less than B diamonds have come from the Argyle mine, and I showed in an earlier slide that most of those have been determined to be eclogitic and are forming at about 1250 degrees Celsius. And we are seeing a lot of mineral inclusions in those stones. And that's certainly helpful to us to know where these diamonds are coming from. In the A greater than B pink diamonds, they have some distinct gemological characteristics too, such as things called rose channels. Now that's named for Gustav Rose, who published about them in 1868 when he was observed them in calcite, but they're present in a lot of other gem materials as well, such as these A greater than B pink diamonds. And what they are is hollow channels that form at the intersection of twin lamellae. And I think you can see on these photographs, you can see the intersection of two different twins, and then right at that intersection, you see that hollow channel where it's at the surface. And so you can sometimes see these quite a lot in these A greater than B pink diamonds, where you can see these hollow channels within the stone. Also, we've done some inclusion analysis on type 2A pinks. This was a continuation of Dr. Evan Smith's work where he was looking at type 2A diamonds and type 2B diamonds, and he discovered that both have a super deep origin. And in this project, we looked just specifically at type 2A pinks. When we realized they were such a large percentage of pink diamonds, one fourth, and there hadn't been a lot published on them, we wanted to learn more about type 2A pinks specifically. And the mineral inclusions that we looked at did show that they have predominantly a super deep origin. and consistent with Dr. Evan Smith's prior work. And one mystery that we still have about these is, while the formation depth is the sublithospheric, it is super deep, we don't know the depth at which the pink coloration came in. Was the diamond color deep at the super deep depths, or at some point did it come up to the same depths where the lithospheric pink diamonds reside and get the pink color there? So that's one of the mysteries that we still have for pink diamonds. So typically, when Raman or photoluminescence maps are collected, then the data are collected from one spot. And recent instrumentation now allows us to collect spectra across the entire diamond surface. Typically best seen is these false color maps. So this new instrumentation is really helpful to us to learn what is the spatial variations that we see in these pink diamonds. They have such pronounced graining and color concentrations, and we want to see what are the other defects that could be affected. And so we wanted to compare the defects seen in the type 1A diamonds that have the color concentrations, and then compare those with type 2A diamonds. So looking at this A greater than B diamond, we see that the photoluminescence mapping exactly mimics that of the pink color. And we can see a similar trend for type 2A pinks that have uniform color. And it also makes us wonder, are there diamonds out there that document the transition between the various groups? Is there an observable transition between the uniform coloration of the type 2A diamonds and then the super straight lines in the A greater than B and the undulating waviness of the A less than B? So we did that. We collected these photoluminescence maps across the whole range of available nitrogen concentrations, and we're showing that full complement of data over here on the right. And based on the PL maps, we determined if the PL was consistent with it being an Argyle type or an A less than B, and on the left side of this diagonal, or whether it was consistent with it being a Siberian type, or if it was a type 2A and had uniform characteristics and should be down here at the origin. And what we realized that there were a few diamonds that had a combination of features. They didn't go well into one specific group or another. And those are plotted here as well. We had a few that were a combination of Argyle and Siberian, and those were rather interesting. But most of them that we saw were down here at low nitrogen concentrations, and that were a combination of Argyle features with type 2, where we saw some areas of uniform coloration, and then we started going to graining, or we saw a uniform pink color, but some of the other defects were starting to segregate into those graining features. So down here at the low nitrogen concentrations, where it's less than about 50 parts per million, that's really where we see this transition from the type 2A diamonds that have very uniform color with the pronounced graining that we see with the higher nitrogen concentrations. So I'm going to switch gears again and talk a little bit about purple diamonds. And what we did was we looked in detail at 50 straight purple diamonds that had, you can see from this collection that what varied most between them is the height of the 550 nanometer band. And you can also see that it has this transmission window in the blue and then one in the red, giving it this purple color. It also has some very small peaks associated with H3 nitrogen. It has a small H3, H4, N3, but not enough to create absorption in that area. And from what we've seen earlier, you can probably surmise that these or most of these are Siberian type, that they are A greater than B. And from looking at the IR in these spectra, that would be correct, that these 96% were Siberian type. And then conversely, we also looked at red diamonds. And we looked at 100 fancy red diamonds in detail. And you can see that all of these absorption spectra are very similar. I could have shown you 100. They would all look very similar to the 3 that I've shown. And you can see that all of them have absorption in the blue. They don't have a transmission window in the blue like the purple diamonds did. And that's what shifts the window over into the red and creates that fancy red color. And as you can probably surmise from what we discussed earlier, is that most of these are A less than B or Argyle type. I'm going to discuss briefly about GOLCONDA pinks. They are very rare in the earth, only about 0.5% of natural pinks. And pink diamonds are rare to begin with, and so we're talking about a very rare subset of a rare class, of a color class. And they are generally pale in color. But where that color comes from is from two centers that are associated with the nitrogen vacancy defect. There's a neutral defect at 575 nanometers and then a negative defect at 637 nanometers. And if that's present in sufficient quantities, it can create a pale pink color in natural diamonds. Among treated diamonds, they are able to introduce much more nitrogen and more vacancies in the raw ingredients that go to create this, and they're able to create much more vibrant pink color in the treated pinks and then the treated lab-grown pinks. Also, what you see in these stones is orange or yellow fluorescence that is directly related to these nitrogen vacancy centers. So this slide, I'm going to try to walk through what the formation process is for these GOLCONDA pinks. Usually the starting material is a type 2A diamond or a diamond with very low single nitrogen. And in most cases it's not even detectable by the infrared absorption spectrometer, but it's still there. And so when this diamond is transported up to the near surface region of the Earth, it can be exposed to natural irradiation. My colleague, Dr. talked quite a bit about natural irradiation 2 weeks ago, and that has to happen within the near surface region. And so that step creates vacancies within the diamond, and that also is a rare process. So we have the rarity of a diamond in which there's still single nitrogen that is surviving in that stone, and then we have the rarity that it was exposed to enough natural radiation to get vacancies in there. And then after it undergoes some low temperature heating within the Earth, those vacancies will migrate to the nitrogens and create the nitrogen vacancy center. So that's what happens rarely in the Earth, and that's what is also the process that treaters will mimic in order to create those treated pinks. One more aspect of pink diamonds that I wanted to mention is a phenomenon that we see in both pinks that are colored by the 550 nanometer band and the GOLCONDA pinks. And that is a temporary bleaching of the color when it's been exposed to ultraviolet. And you can see, like in this example, that the color change can be quite dramatic. But it is fully reversible, and the stable color is fully recoverable as well. But it is something that can happen if a pink diamond is exposed to the ultraviolet. And for further reading, I want to encourage you to look at the winter 2018 issue of Gems in Gemology. It is freely available on the GIA website, and it has also a lot of good information about pink diamonds. So thank you very much for your time and attention, and I will be happy to answer some questions.
Okay, great, Sally. Thank you very much. That was very good, or as we say here, flawless. One question we got quite a lot of was, with the Argyle mine closing, what do you think might be the next big deposit of pink diamonds?
Well, I think I don't know if there will be another pink deposit that will replace the Argyle. I don't know if we'll find another mine that has those very special characteristics, that has the A less than B. And because most other pink diamonds that we have found are the A greater than B. So it looks like the Argyle mine is very special, and it looks like it'll be difficult to duplicate any of the diamonds that are found there. The fancy reds, some of the orangey pinks, certainly the violets that are in a different color family, but they're certainly specific to the Argyle line. It may be difficult to find a place that will, to find a locality that will replace the Argyle line.
Okay, thank you. Can you talk a little more about detecting color treatment of pinks and maybe what sort of color treatments are available to treat pinks or to pink?
Okay, sure. There's a number of different ways. That animation that I gave near the end, in which we have single nitrogen and then we have vacancies, and then you put those together to create the NV center. That's the most common way to treat diamonds to a pink color. Typically, in the case of lab-grown diamonds, they have nitrogen included within the growth process so that, and since they're young diamonds, they are already as single nitrogen. So for the lab-grown diamonds, they have single nitrogen, they need to irradiate them to inject the vacancies, and then they need to give it low temperature annealing. Typically it's about 600 degrees Celsius to get those vacancies moving, and then they'll pair up with the nitrogen to create those nitrogen vacancy centers. In natural diamonds, you want to start off with single nitrogen, and that's somewhat rare to come by among natural stones. So what a lot of the treaters will do is they'll HPHT treat those natural stones first, those type 1As, and what the HPHT treatment does is it takes those nitrogen pairs, those A aggregates, and it'll split those apart, so then you'll have single nitrogen. And up at the very high temperatures and pressures that is for HPHT annealing, those A aggregates will want to go apart. For the natural stones at 1000 degrees Celsius, it's a one-way street. The A aggregates won't back dissociate to single nitrogen, but that can happen up at HPHT temperatures and pressures. So they'll HPHT treat the diamonds to create single nitrogen, and then the process is the same from there, where they'll give it some irradiation and then some low temperature annealing. Another aspect that can be done is that they can take brownish pink diamonds that are type 2A, and they can HPHT treat those. The idea is to try to reduce the brownish component and preserve the 550 nanometer band or in the pink color. And so that treatment is possible among the 550 nanometer band diamonds, but most times the treatments to create pink color are just from generation of NV centers.
Great. Do the Argyle stones have a different color of UV fluorescence under long wave than Siberian diamonds?
Not to a great extent. We don't often look at them under UV or under very strong UV just because of that bleaching effect. And so the only reason, so we will generally only look at them under, say, the diamond view illumination if there is something that we're concerned about with treatment. But in terms of what we're looking at for long wave versus under long wave UV, we don't see a lot of distinguishing characteristics for that.
Okay. How long does it take to bleach a pink diamond under UV and, you know, under, let's say, both UVs, maybe long wave and diamond view?
Okay. With the diamond view, since that's a much higher energy and a much shorter wavelength, that can pretty much happen while we're collecting the images. Now, keep in mind that this bleaching is temporary. It'll go back naturally over time, over a day or two, to its stable color, and you can speed that up by putting it under a white light. If you put it under long wave, the effect is much less, and it would have to be under the long wave UV for much longer. So, but it is still instantly recoverable very quickly. I usually would get these under a white light and bring them back within 10-15 minutes if I need to diamond view a stone.
Okay. What fully is the difference between rose channels and etch channels?
that might be a good question for you to answer, Troy. You've done a lot more with them.
Okay, sure. I'm happy to answer that. So etch channels form when the diamond is growing. If you get a crystallographic defect or a stacking fault, that will grow in weakness into the diamond lattice. And then when the diamond is in harsh geologic fluid, it can actually etch away at that weakness and leaving a channel, hence the name etch channel. A rose channel, by contrast, occurs when the diamond gets plastically deformed in one direction and then at an opposing direction, and it sort of opens up a channel. So a rose channel is caused by deformation and an etch channel is caused by etching. And then, let's see.
Thanks for taking that question, Troy.
No problem. Does Golconda pinks refer only to Indian diamonds mined from the Golconda source, or would we apply it to any diamond with a similar chemical property, i.e. ones colored by NV centers?
That's a good question, and I should have made that clear during the time. Yes, that was originally started where any type 2A diamond was called a Golconda, and then and since most of these diamonds were pink, they became known as Golconda pinks. But it's pretty much any diamond, regardless of its source, regardless of its locality, that gets its color from nitrogen vacancy centers. So it had its origin in the Golconda region, but it now just is a general term applied to all type 2A pinks that have their color due to nitrogen vacancy centers.
Right, and a follow-up question, why do Golconda pinks fluoresce orange or red?
Well, because they have those very strong peaks that are associated with the nitrogen vacancy centers, and those can both absorb at those wavelengths, but they can also emit. And so just like an N3 center will cause absorption in the near end of the blue, it'll also cause a fluorescence within the blue itself. And so we see the same thing with nitrogen vacancy centers, where we can see both absorption and emission from the same defect. The variations that we see within the fluorescent color depends on the relative concentration of the NV neutral versus the NV minus, and depending on how the relative concentrations will determine the fluorescence color that you see.
Great. Are there any other pink diamond sources that you know of that follow a similar scheme of A greater than B, A less than B, or type 2A?
Well, there are a number of localities around the world that do give the A greater than B diamonds. The one that has the highest production is the ones in Siberia, the Lomonosov mines in Western Russia. Those have also been studied, particularly by our colleague, Dr. Karen Smit. I don't believe she was able to do the diamond typing on them, but from what we gather is that those are most likely A greater than B. And and as far as the type 2A diamonds, there's a number of them that we've heard about have come from Tanzania and then some from South Africa, but we're not fully sure about where all of the localities are for those. It will be interesting to see in the next couple of years after the Argyle mine closes, what sort of shifts we see in the pink colors that are on the market.
Okay, great. That about does it for the questions we have. If you have any other questions, please find us on Instagram, Facebook, LinkedIn, and Twitter. I would like to thank you all for coming, and please join us next week where we'll be joined by Dr. Evan Smith, who will tell us about the history of diamond cutting and polishing. Thank you.
Thank you. Thank you very much.